Here's answers to the 11 multiple choice of the Kinetics Summative. Question 1 wants us to use this data and determine which rate law is consistent with the data. Now, normally I would like to see some graphs. I'd like to look for a linear graph. If the concentration versus time graph is linear, it's 0 order. If the natural log graph is linear, it's first order. And if 1 over the concentration is linear, it's second order. I don't have that. So then without graphing, I just want to see like which one would be linear, which one would have a constant slope, or which one would always change by the same amount every 100 seconds. And so I can kind of just look at by inspection at the first two, the concentration and the natural log of the concentration, and I can see that they don't always change by the same amount, but the 1 over concentration data does. Every 100 seconds, it goes up by 0.75 units, which would then eventually give me a graph with a constant slope. So then I can determine that it's second order, the way we would write it as like R the rate equals K the constant times the concentration of my reactant, and then second order, we would put that in as an exponent of 2. Sometimes people pick C or B, and I think that they knew that it was probably the second order, and then just kind of missed how that would be written as a rate law. So you interpreted the data correctly, so that's good. And then I would just say, oh, bonehead, that second order should be shown as an exponent of 2. Question number 2 gives you a lot of data for a pretty simple question. So we've got this reaction, NO reacts with oxygen, producing NO2. They're showing me the first graph of how the concentration of the NO reactant would decrease over time, which it would. Obviously, the reactants are consumed over time, so the concentration should decrease. Well, then they want to know which graph best represents the changes in concentration of the oxygen. So the oxygen would be the other reactant. It should decrease over time. It would also be consumed. But do you kind of notice, even by looking at the initial concentrations, that the concentration of the NO is double that of the O2? That what they started with actually matches the ratio in the balanced equation? That when we look at these reaction rates for reactants and products, they should match the ratio in the balanced equation. So I should be consuming the NO2 at double the rate that I consume the oxygen. So at any point in time, the concentration of the NO should be double that of the O2. So you could pick any point in time, I mean the initial, or even like if I pick at 100 and I just kind of estimate, like at 100 seconds, the NO is like 0.0005 moles per liter. And I can kind of estimate on graph 1, the concentration at 100 seconds for oxygen is like half. So it should be graph 1, because the rate of the oxygen consumption is half the rate at which NO is consumed. It should match the ratio from the balanced equation. Question 3. I've got 2 diagrams that represent collisions between carbon monoxide and nitrogen dioxide. We want to know which diagram most likely represents an effective collision and why. Now, there's a couple of different ways that you could think about this, but we kind of mentioned that particles need to collide with sufficient energy, and they need to collide with proper orientation. So if I think about these molecules, the dark atom is the oxygen. So these would be oxygens. I guess I already wrote one oxygen in there. This would be like an oxygen, and these would be the oxygens. That's another oxygen, I guess. And then this would be a nitrogen too. So if I label all those atoms according to that little key, and then I think about these molecules. Of all 3 atoms, oxygen's got a pretty high electronegativity. So the oxygen's going to tend to pull on the electrons. So the oxygen's going to pull on electrons from carbon. meaning the oxygen end would be a little negative and the carbon end a little positive. Well, same thing's going to happen with the NO2. Oxygen's electronegativity is a little bit higher than nitrogen, so he's going to pull on those electrons, making the oxygen a little bit negative. And so one thing that I would think about when I'm looking at an effective collision, when the particles have to collide in proper orientation, I would want like a partial negative to collide with a partial positive, which is kind of shown in diagram 1. That's when I'd likely actually have a reaction or a collision that results in a change, in new products being formed. In diagram 2, the carbon is going to be partially positive, and so is the nitrogen. So I don't know if that would be like the most effective collision. So we want something about diagram 1 being the best collision, but it really doesn't have anything to do with like the same size and same energy or larger rate constants. It's about the particles colliding in proper orientation to form a new bond, and hopefully they would have sufficient energy to overcome the activation energy barrier. Or in other words, enough energy for the particles to form new bonds on the product side. But that's always one thing that I think about, that a good collision should have partial positives and partial negatives colliding with each other. 4, I've got solid of varying particle sizes and varying temperatures, which represents collisions that would result in the fastest reaction rate. So we obviously want the largest temperature, where the particles have the most energy and they're colliding more often. And I also want the smallest particle size. When there's more surface area, there's just more chances for particles to collide. And that should also result in a faster reaction. Think about like dissolving a big sugar cube versus like granular sugar. I mean, I could put granular sugar in water and mix it around. It should dissolve really quickly because there's more surface area exposed to the water molecules. But if I had a larger sugar cube, it's just going to dissolve on the outside of the cube and it would take slower. 5, here's a visual of a 3-step reaction. We want to know which represents an intermediate. Intermediates are particles that should be formed and consumed. Now, technically, there's probably 2 intermediates. There's that one in step 1, where there's like 2 gray atoms and 2 dark atoms. That would cancel in step 2. And then there's another intermediate from step 2 to 3. 1 dark atom and then 2 gray atoms. So choice D would be the best representation here of an intermediate, even though there's technically 2 of them. 6, which of the following initial rate law expressions is consistent with the proposed mechanism? Okay, so we know that in the lab, if I try this reaction, the final rate that I experience in the lab with my data is really going to be dependent on the slowest step of the mechanism. We call that the rate determining step. So it's step 2. And normally then we would write a rate law based on the molecules colliding of that slow step. The only problem here is that the slow step involves an intermediate. And we can't study intermediates. We don't have control over intermediates in the lab. So we don't put them in our expressions, in our rate law expressions. But if the first step is an equilibrium, a reversible reaction, we can just take what's opposite the intermediate and substitute it in replacement of that intermediate for step 2. So I would have 2 of the NOs, or NO to the second power, and then I would still have that hydrogen to the first. Rate law is always based on the slowest step of the mechanism, but you can't use intermediates. So you'd have to replace whatever is opposite the intermediate in that reversible step. 7, here's a graph of temperatures, molecules with different amounts of energies because they're at different temperatures. Based on the diagram, at which temperature will the reactant be consumed at the fastest rate? This question, I don't know if anybody missed this one. Obviously, it's temperature 4. It's the highest temperature because on average, most particles have the largest amount of energy. The Y part has to do with the activation energy barrier. At the higher temperature, obviously particles are moving around faster and they're colliding more often, but there's also more particles that are at or above that activation energy point. So if there's more particles with sufficient energy to run the reaction, it should go at a faster rate. Number 8. The reaction below takes place in 2 elementary steps. Which of the following statements is correct? So I'm looking for the equation for step 1 and the overall rate law. Well, this time they give me the overall reaction, and I kind of have to like piece this together backwards to figure out what would be the reactants and products of step 1. So in other words, I want 2 molecules of NO2 on the reactant side. I've got 1 in step 2, so I need to add another one to my step 1 of the mechanism. I want that F2 also on the reactant side. Here's my overall equation, but it's not in step 2, so I need to put that in step 1. So it appears in the final balanced equation. Also, on the product side, I want 2 of these NO2Fs. Well, in step 2, there's only 1 of them, so I'll need to add another one to step 1. The last piece of the puzzle is that we don't want that random fluorine atom in my final balanced equation. So if it's showing up as a reactant in step 2, it must have been produced in step 1. It's an intermediate. If it's produced and consumed, that'll cancel out. So I got the expression or the equation for step 1, and then the rate law would be based on the molecularity of the slow step, which would be step 1. So it should be first order for both the NO2 and the F2. Number 9 kind of brings us back to our bonding days. We've got bond energies for this pretty simple reaction. Now, bond energy is defined as the energy that I have to add to break a bond. So I can add it up for the reactant side. I need to add energy to break apart 1 mole of hydrogen bonds and 1 mole of those chlorine-chlorine bonds. That's going to require about 670 kilojoules. Well, now on the product side, technically I'm not breaking these bonds, I'm forming the bonds. There's going to be 2 moles of HCl, so I take 2 times that 430, and initially I get this 860. Well, the only problem is that I'm not going to add that amount of energy. I'm not breaking the bonds, I'm forming the bonds. So I want to make that one exothermic or negative. Endothermic to break the bonds, exothermic when bonds are formed. So I can see that it's going to be exothermic. So my product should be at a lower energy level than the reactants. The difference should be 190 kilojoules. So something like B, where my products are lower by a net release of 190 kilojoules. And then the last 2, 10 and 11, both go back to this same set of data. When free chlorine atoms encounter ozone molecules in the atmosphere, the following reaction mechanism is proposed to occur. In question 10, which of the following rate laws for the overall reaction corresponds to the proposed mechanism? So if this mechanism is correct, then if I go in the lab, the rate law should match the rate law based on the molecularity of the slow step, or the molecules colliding of the slow step. It should be first order for the chlorine and first order for the O3 ozone. Then I really like this last one. Question 11 says, okay, so then which of these energy profile graphs would best correspond to the proposed mechanism? Well, it was a two-step mechanism, so it should have two humps, so not C. Then other little things that I want to pull off of this data. Number one, it's overall exothermic. The delta H is negative, so my product should be at a lower energy level than my reactants. And I noticed that step 1 is the slow step. What makes it slow? It's probably got a higher activation energy. So I want a two-step mechanism that's exothermic, so not A. A would show that the products are at a higher energy level. Not that one. My product should be lower, and the activation energy for step 1 should be higher than step 2. So something like D. In choice B, here's like the activation energy for step 1, but then here's the activation energy from step 2. Step 2 would have been the slower step if something like B were correct. So choice D for the win.